Okay, so my name is Duro Diaz, and I am going to present the first results we obtained in the project named towards high-fidelity simulations of urban flows. This will be the outline of the presentation. And to begin, cities have been regarded as centers of economic and demographic growth. For this reason, it is expected that in the upcoming years, there will be an increase of population in the city cores. In fact, the United Nations predicted that by 2050, there will be 2/3 of the global population living inside cities. So, because of the increasing problem of the climate change, the number of heat waves will increase both in number, both in intensity and in frequency. So amplifying, which is known as the urban heat island effect, which is understood as the phenomena in which the temperature inside a city is warmer than at its surroundings because of the human activity and also poor air ventilation because of the buildings. So it is very important to improve the urban climate forecasting in order to reduce the effects of these heat waves periods, and also in the future it can be also used in order to help in cities planning and also to detect episodes of high pollution. On the other hand, thanks to the emergence of artificial intelligence, we can use data-driven models in order to obtain faster results. But these models need accurate databases which can be relied. Finally, after reviewing the literature, it has been seen that the state-of-the-art of the industry uses runs, which is a kind of simulations with low accuracy because they are not able to capture the unsteady phenomena around of the flow around the buildings. So a better option is using LES because it improves the accuracy, but its counterpart is that the computational cost is bigger because bigger meshes are needed since they need a bigger resolution in order to solve the flow. So the main goal of the present work consists in taking advantage of the new PREX-scale computers by using a CFD algorithm, which has been developed in order to exploit the emerging HPC architectures based on GPUs. And to do so, we will set up a high-fidelity numerical framework in order to obtain accurate predictions of the full-scale urban flows. Then we will validate it by comparing the results with wind tunnel data. And finally, we will analyze the complex physics that are present inside a city because the interaction between buildings. So LES is more computationally expensive because it only models the dissipative ranges. To do so, spatial filtering is applied to the Navier-Stokes equations, and these scales are modeled with a subgrid stress tensor. Then the turbulent viscosity is modeled with the Bremen eddy viscosity model, and finally, in order to solve the near wall region on the ground, we use a wall model with this equation. So in a realistic scenario or in complex geometries, LES is very computationally expensive. So this kind of simulation can only be done in supercomputers. So SOT2D is a CFD algorithm which takes advantage of the novel HPC architectures based on GPUs in order to solve both compressible and incompressible flows by using DNS and LES. Its main features are the following. It is a high-order spectral element method, which uses the Lobato-Gauss-Legendre quadrature, in order to avoid aliasing. besides of the skew symmetric splitting of convective terms, which also helps to reduce the computational cost. And in order to introduce the lowest amount possible of viscosity into the system, the lowest amount of dissipation into the system, it uses a variable diffusive viscosity. And finally, for the incompressible case, the temporal integration scheme is the one presented in the slide. Next, regarding the stability of the code, in the next talk, Jordi Muela will dig deeper in details, but in this slide, we can see a plot of the speed up of SOT2D with a study which has been carried out in Mare Nostrum 5, which uses H100 GPUs. It shows a quasi-linear behavior up to 128 GPUs for a 1.300 million degrees of freedom mesh. On the other hand, regarding the iteration wall clock time, in the lower part of the graph, we can see some test cases that were done in Mare Nostrum 5 by using float precision, and the two cases, the results of the two cases we simulated, and for the case number 1, the results are at the upper part of the graph because we used doubles precision. So the numerical setup of our simulations is the following. First of all, we want to introduce an ABL, an atmospheric boundary layer profile into our system, which is modeled by this equation, which depends on the U star, the von Karman constant, and the roughness length. Then our domain is divided into two subdomains. And first of all, the precursor is used in order to allow the free development of turbulence of the atmospheric boundary layer. To do so, we use a periodicity in the inlet and outlet, and also in the laterals of the domain. Besides, we use a wall model on the ground of the precursor. And one thing we observed in preliminary simulations is that the length of the precursor must be at least 6 times the height of the domain, because otherwise, if the characteristic length of the turbulent structures was higher than the precursor length, we recycled the same structures and we didn't have the desired results. Moving into the principal domain, the value at the outlet of the precursor is injected into the inlet of the principal domain. And the principal domain contains the city, and we impose a wall model on the ground of the domain, but in the buildings, we impose a non-slip boundary conditions because it is a zone with detachment and reattachment of the flow. In order to validate our results, we used two cases with experimental results of increasing complexity. For the first case, it consists in a matrix of 7 by 7 cubes with a height equal to 30 meters, and both the inlet conditions, and the length of the domain are the same as the ones from the experiment. But in the second case, which is known as setval, the inlet conditions are the same as the ones in the experiment, but we had to increase the height of the domain as well as the distance from the inlet into the city and the distance of the inlet of the city to the outlet, because otherwise we had blockage of the flow around the city. And in the second case, the complexity is bigger because it tries to replicate the shape of a European city with flat roofs. So moving into the results section, in order to solve the first case, we used 3 meshes of increasing complexity. Regarding the city resolution, it involves the city itself up to height equal to 30 meters. Then the resolution of the precursor was also increased because the two subdomains are coupled. So it was needed in order to solve correctly the AVL in this subdomain. Finally, the three meshes are of fourth order and using hexaedral cells. Next, regarding the fine mesh with which the results were obtained, these results were obtained in 7.5 days and using 16 GPUs. The total integration time was 7 hours, being equivalent to 40 flow-throughs. In order to check the temporal convergence of the system, first of all, we checked the U star at the precursor, which is equivalent to the friction velocity in a channel. And also, we assessed the streamwise velocity at different stations of the domain and at different flow-throughs. Can be seen in this case that from 20 flow-throughs onwards, the temporal convergence was reached. Then, in order to validate the results, we use the streamwise velocity profiles. It can be seen that the results match quite good with the experiments, both for cores and fine meshes. So the validation is successful as our numerical setup captures correctly the behavior of the flow at the inflow region, at the top of the, inside the cavity, inside the first cavity, also at the top of the last row of cubes, and in the wake of the domain. And from a more qualitative point of view, we also observe flow features observed in literature, which are a flow separation, a recirculation bubble over the top of the first cube, also the recirculation strength in the first cavity being higher than in the other cavities, and the attachment and reattachment length after the last row of cubes. To end with the results of the first case, we assessed the turbulent kinetic energy. Here, the results match quite good with the experiments, both for, in fact, they are very similar, the results obtained with a coarse and a fine mesh. And also, we see that the peak of turbulent kinetic energy is found over the top of the first cube and inside the first cavity. So the first case has been successfully validated. Moving into the second case, we also used 3 meshes of increasing refinement, and to have consistency, we tried to maintain the same number of degrees of freedom for the 3 cases. Regarding the city resolution, in this case, it involves the city and up to 24 meters, and as the complexity of the city in this case is higher, a bigger number of nodes was located inside the city in order to capture well the features of the city geometry. So we had to save nodes at the outer part of the domain, so we had to reduce the resolution in the precursor, but being fine enough in order to solve correctly the atmospheric boundary layer. In this case, the results were obtained in 4 days using 32 GPUs, and the total integration time were 4 hours and 15 minutes, which is equivalent to 20 flow-throughs. In order to validate this case, we used the streamwise velocity once again at different locations, and we see that the results match almost perfectly with the experiments once again for both fine and coarse meshes. So we are able to capture the flow at different locations in an open region, over the top of a building, or in the cavities between 2 buildings. So the numerical framework is good enough in order to capture the flow behavior in more complex cities. So the main conclusions of this work are that we performed simulations of full-scale urban geometries, which has been validated by using wind tunnel results and validating the first and second order statistics. Also, that from a qualitative point of view, the main features of the flow field were correctly captured. And thanks to SOT2D being a high-order method, we were able to obtain a good accuracy even when using a coarse mesh. Finally, when using GPUs, the hold time needed to reach temporal convergence reduces because the SOT2D is able to take advantage of the novel HPC architectures based on GPUs. And to end the presentation, the next step will be performing simulations around the city of Barcelona. The first simulation that we are doing consists in a 1.5 by 1.5 kilometer square of the surroundings of UPC Campus North. And the next, we will try to find an average wind direction and an average atmospheric boundary layer profile in order to validate our results with real proofs located around the buildings of the Campus North. And that's all. Thanks for your attention.
Thank you very much.